Elimination reactions via E2 mechanism generate alkene products containing a pi bond. Elimination reactions via E2 mechanism can also be used to synthesize alkynes containing two pi bonds. The difference between alkyne synthesis and alkene synthesis via E2 mechanism is the starting material. The reactant has to be a dihalide, an alkyl dihalide. So for alkyne synthesis, you need an alkyl dihalide, whereas in alkene synthesis, you need an alkyl halide. And so you're going to need a reactant containing two halogen atoms bonded to the carbons. And in order for alkyne synthesis to work, you're going to need two elimination reactions. So two elimination reactions are needed in order to remove 2 moles of hydrogen halide from a dihalide substrate. And that results in the synthesis of alkynes containing a triple bond. And there are two different kinds of alkyl dihalides. There's vicinal dihalide and geminal dihalide. In a vicinal dihalide, you have the other halogen bonded to the adjacent carbon. And so you have one halogen bonded to carbon 1, which is an alpha carbon, and then the other halogen bonded to the second alpha carbon. So now you have 2 alpha carbons here. In geminal dihalide, you have both halogens bonded to the same carbon atom, and so you only have 1 alpha carbon in this case. So that's the difference between a vicinal dihalide and geminal dihalide. And so looking at vicinal dihalide here, the first elimination reaction results in the formation of an alkene, a double bond. And then the second elimination reaction results in the formation of the alkyne. Same goes for a geminal dihalide. So an amide or a strong base deprotonates a hydrogen, which results in the cleavage of this sigma bond between the carbon, the alpha carbon, and the leaving group, which results in the formation of a pi bond. And then the second elimination reaction results in the formation of the second pi bond. So now you have 2 pi bonds, which are contained in a triple bond in alkynes. So here's a reaction mechanism showing you the movement of electrons in an E2 reaction involving a vicinal dihalide. So you can see here that a strong base deprotonates this hydrogen, which results in the formation of a pi bond and also the cleavage of the sigma bond between the carbon and the halogen. And then the second round of elimination reaction occurs. Again, a strong base deprotonates this hydrogen, which results in formation of the second pi bond and the cleavage of the second halogen. And this results in formation of a triple bond, which is the alkyne. And down here is the reaction mechanism for an E2 reaction involving geminal dihalide. So you can see you have a strong base here that deprotonates this hydrogen, which results in the formation of the first pi bond and the cleavage of the first halogen. And this results in the formation of alkene. And the second round of elimination reaction deprotonates this hydrogen right here, resulting in the formation of the second pi bond and the cleavage of the second halogen. And this results in the formation of the alkyne. So I mentioned earlier that in order to synthesize alkynes, we're going to need stronger bases. Bases that are stronger than the ones that we use to synthesize alkenes from alkyl halides. Both sodium amide and tert butoxide are strong enough, and they're actually commonly used in alkyne synthesis. The reason why we use stronger bases is because of the second round of elimination. That involves a double bond, a stronger sp2 hybridized carbon to hydrogen bonds. So here are 2 examples of the hydrohalogenation of dihalides to form alkynes containing 2 new pi bonds. So the first one here involves a geminal dihalide, and this results in formation of the triple bond. The second example here involves a vicinal dihalide, which also results in formation of the triple bond. And here's practice problem number 21. Draw the alkynes formed when each dihalide is treated with excess base. So an easy way to do this is to locate the dihalides. And so once you've located the two halogens, then all you have to do now is add a triple bond in between those two carbon atoms. And so the first one here, we have the two halogens right here. And so if these two halogens are cleaved along with the hydrogen atoms here and here, what you have is a triple bond. And so we're going to have a triple bond 1, 2, and 3. And that's it. So that's the result of the formation of the alkyne product. And here we have a geminal dihalide. So we have 1, 2 halogens here, and then we also have 2 hydrogens right over here, the beta hydrogens. And so if these 4 atoms get cleaved, then what we have is a triple bond between this carbon atom and this carbon right here. One, 2, and 3. And for the third alkyl halide here, we have another geminal dihalide. So we can go ahead and circle these. And we have 1, 2, and 3 hydrogens right here, and 2 hydrogens over here. And so because we have 2 different beta carbons, we're also going to have 2 different beta hydrogens. And so in that case, we're going to have 2 different alkyne products. So the first one is going to be a triple bond between the second carbon and this third carbon over here. And the other alkyne will contain a triple bond between the first carbon and the alpha carbon. And so the first one has a terminal alkyne right here. And the other one is going to be an internal alkyne. So 1, 2, and 3. There it is. So this is called a terminal alkyne, and this is called an internal alkyne. So let's put a plus sign here. And for the last dihalide here, we have a vicinal dihalide. So the bromine, the 2 bromine atoms, along with the 2 hydrogen atoms, will be cleaved. And what's left is a triple bond. So how do we differentiate substitution reaction from elimination reaction? I mean, there's 4 different mechanisms here. There's SN1, SN2, E1, or E2. So there are 2 things that we're going to take a look at here. The first one is the nature of the nucleophile. And then the second one is the nature of the alkyl halide itself. So let's take a look at the first one here. It says, good nucleophiles that are weak bases favor substitution over elimination. So good nucleophiles such as iodide ion, bromide, bisulfide cyanide, and acetate ion are all considered good nucleophiles that are weak bases, because you don't want to use strong bases. Strong bases will favor elimination reaction. And so the weak bases that are considered good nucleophiles will favor substitution over elimination. So here's an example. We have a primary alkyl halide here reacting with a good nucleophile, which is considered a weak base, in a polar protic solvent. And you have a backside attack, and the sigma bond breaks between the carbon and the bromine atom. And what results in is the formation of the alkyl halide, the substitution product. So the second part here involves the nature of the base. So bulky non-nucleophilic bases favor elimination reaction over substitution reaction. And so bulky bases such as those containing tert-butoxide ion, DBU, DBN are too sterically hindered to even attack tetravalent carbon. And so they'd rather attack a smaller group connected to the carbon, which is normally a proton, the hydrogen. And so this favors elimination reaction over substitution reaction. So here's an example of an elimination reaction involving a strong non-nucleophilic base, which is a tert butoxide. So this tert butoxide ion will deprotonate this hydrogen, which results in the formation of the double bond and the cleavage of the sigma bond between the alpha carbon and the bromine atom. So the result is an elimination product. And so again, when determining or predicting the product of any of these four reactions, we have to use these two steps right here as our guide. So the first step is to classify the alkyl halide. Do we have a primary, a secondary, or a tertiary alkyl halide? And then we have to look at whether we have a base or a nucleophile. Do we have a non-nucleophilic base or a nucleophile? And then we have to identify whether we have a strong base or a weak base or a bulky base. Same thing for the nucleophile, the nature of the nucleophile. So here's a table that basically summarizes the four different reaction mechanisms. So we have substitution reaction versus elimination reaction. So one important thing that you need to look at is the nature of the alkyl halide. Do we have a primary, secondary, or tertiary? And then after that, you have to look at the nature of the nucleophile or the base that's being used. So if you're using a nucleophile, then we have a substitution reaction. If you're using a base, then we have an elimination reaction. So notice that for the alkyl halide here, it could either undergo SN2 reaction or E2 reaction. And so if you have a strong nucleophile, that's going to undergo SN2 reaction. If you have a strong non-nucleophilic bulky base, then that's going to undergo E2 reaction. And when you look at the tertiary alkyl halide here, you can see that if you use a strong base, then the alkyl halide will undergo E2 mechanism. However, if you use a weak base and a weak nucleophile, then you're going to have two different mechanisms happening here. You can have an SN1 product and an E1 product. So you can have a combination of different products here. For a secondary alkyl halide, if you were to use a strong non-nucleophilic bulky base, then you can also get an E2 product. However, if you're using a strong base and a strong nucleophile, then you can have a combination of SN2 and E2 products. And finally, if you have a weak base and a weak nucleophile, then you can have a combination of SN1 and E1 products. Again, that's for a secondary alkyl halide. So first, let's take a look at tertiary alkyl halides. So if we have strong bases, then you know that we're going to have an elimination reaction. More specifically, E2 elimination reaction. So we have a tertiary alkyl halide right here, which reacts with a strong base. And if we have a strong base, then it will deprotonate a beta hydrogen that's bonded to a beta carbon. And so the result is the formation of a double bond, which is an alkene. However, if we have a weak nucleophile or weak bases reacting with a tertiary alkyl halide, what we get is a mixture. It's going to be a mixture of SN1 and E1 products. So again, we get an E2 product for a reaction between a tertiary alkyl halide and a strong base, whereas for a tertiary alkyl halide and weak nucleophiles or bases, we get a mixture of SN1 and E1 products. And for primary alkyl halides, if we were to react a primary alkyl halide with a strong nucleophile, then you know that we're going to have a substitution reaction. More specifically, SN2 reaction. So again, if we have a nucleophile, then we're going to have a nucleophilic substitution reaction. And if we have a primary alkyl halide, this is going to undergo SN2 reaction. So we will have an SN2 product. So there's going to be a backside attack, which results in inversion and also the cleavage of this sigma bond between the electron deficient carbon atom and the leaving group. On the other hand, if we have a primary alkyl halide reacting with a strong bulky base, then what we have is an E2 elimination product. So we have a strong bulky base, which will then react with a proton on a beta carbon. And so if this is the alpha carbon right here, then we will have a beta hydrogen right here, which will then react with the bulky base. So the bulky base can't react as a nucleophile because it's too bulky. It can't attack the electron deficient carbon via backside attack. And so it has to react as a base via an E2 elimination reaction. And here are the products once again. If we have a strong nucleophile reacting with a primary alkyl halide, the result is an SN2 product. On the other hand, if we have a primary alkyl halide reacting with a strong bulky base, we get an E2 elimination product. Predicting the products of reactions involving secondary alkyl halides is a little bit more challenging. And the reason why is because secondary alkyl halides can undergo reaction via SN1, SN2, E1, or E2 mechanism. And so if you have a secondary alkyl halide reacting with a strong base, which also counts as a strong nucleophile, then what you have is a combination of E2 and SN2 products. However, if you're only reacting the secondary alkyl halide with a strong bulky base, then what you get is a single product, which is an elimination product, more specifically E2 elimination product. So again, if you have a secondary alkyl halide and you react this with a strong base, which also counts as a strong nucleophile, then what you have is a mixture of products, a mixture of SN2 and E2 products. On the other hand, if you react the secondary alkyl halide with a strong bulky base, then this reaction will only undergo elimination reaction, in which the product is an E2 elimination product. And finally, if you have a secondary alkyl halide reacting it with a weak nucleophile, which also counts as a weak base, then you'll also have a mixture of products, a mixture of SN1 and E1 products. So we have a secondary alkyl halide reacting with a weak nucleophile, which is also considered a weak base, and what results is the formation of a mixture of SN1 and E1 products. So here's practice problem number 22. Draw the products in each reaction. So whenever you're looking at a chemical reaction, the first thing that you want to do is to identify the classification of the alkyl halide. So the very first one here is a primary alkyl halide. So let's go ahead and write that down. And then we're going to identify the nature of this compound here. Is this a base or is it acting as a nucleophile? And you can see that this is a tert butoxide ion, and so this is going to act as a strong base. And so a strong base reacting with a primary alkyl halide will result in the formation of an E2 elimination product. And so we're going to have an alkene here. So let's see, we have 1, 2, 3, 4, 5, 6, 7 carbon atoms. 1, 2, 3, 4, 5, 6, 7, and then there's going to be a double bond right over here. Alright, so that's going to be the product of this elimination reaction. And for the second chemical reaction here, we have a secondary alkyl halide. So we can go ahead and write that down. And then this one, this is a hydroxide ion. So this is a strong base, which can also act as a strong nucleophile. And so this is both a strong base and nucleophile. And so because of that, we're going to have two different products here, an SN2 product and an E2 product. So what would an E2 product look like? Well, if we were to remove this chlorine atom and remove one of the hydrogens on the beta carbon, we can have two elimination products. But according to side-step rule, the major product is going to be the one that's more substituted. And so we will have a double bond right over here between this beta carbon atom and the alpha carbon atom. So one of the elimination product will be a trans alkene. And so this is the E2 product. So I'm just going to write down E2 here. And this one right here is also an E2 product, plus the SN2 product. And so the SN2 product is basically, we're basically just replacing this chlorine atom with the hydroxide, a hydroxyl group. So this is going to be the SN2 product right here, and the E2 product. And of course, this product for the E2 is the major product, and the reason why is because we have a trans alkene here. So the minor product is going to be a cis alkene. And for the third chemical reaction here, we have a tertiary alkyl halide because it contains 1, 2, 3 carbon atoms bonded to this carbon right here. So we have a tertiary alkyl halide, and this ethanol right here is acting as a weak base and also as a weak nucleophile. And the reason why is because it is neutral. It doesn't have a negative charge. And so because we have a weak nucleophile and also a weak base, and then we have a tertiary alkyl halide here, this reaction will undergo E1 and SN1 reaction. So first, let's take a look at the product of an SN1 reaction. So if we have an SN1 reaction, then all you have to do is replace this iodine atom. So we're going to substitute this for the nucleophile. And so what we have is this SN1 product right here, which is basically an oxygen, CH2CH3. Alright, so this is a product of the SN1 reaction. And then for the E1 reaction, since we have multiple beta carbons here, we have 1, 2, and 3. And you know that this carbon right here and this other carbon here, they're basically the same beta carbon. And so we're going to have two different products of E1 reaction. And so what would that look like? So the first elimination product would look something like this. So it's going to be a double bond between the alpha carbon atom and this beta carbon. And so we have a cyclohexane ring here, and then a double bond here. So you can see that this is a tri-substituted elimination product. And let's take a look at the other one. Another cyclohexane ring here. And then the other double bond will be between this beta carbon here and the alpha carbon. And so what we have is a tri-substituted alkene. So we have 1, 2, 3. So this is tri-substituted, and then this one is 1, 2, 3. This is also tri-substituted. So they are actually equally stable. All right, and so so we'll write E1 product for this one and this one as well. And for the last reaction here, you can see that we have a tertiary alkyl halide. So we can go ahead and label this tertiary. And then this one right here, this is an ethoxide ion, which is actually a strong base. So this is a strong base. It contains lone pairs of electrons. And because we have a negative charge here, this is also a strong nucleophile. However, we have a tertiary alkyl halide, and so this is not going to undergo SN2 reaction, because for SN2 reaction to work, you have to have either a secondary alkyl halide or a primary alkyl halide. So in this case, the alkyl halide here is too bulky for this strong nucleophile, and so it's not going to react via SN2 reaction. It will only react via E2 elimination reaction. So what does the elimination product look like? What does the E2 product look like? So when you look at the nature of this alkyl halide, you can see that it contains multiple beta carbons. All right, so let's label the beta carbons here. We have this beta carbon, this one right here, and the third one right here. But you can see that the first two over here, they're actually similar because they're both primary carbons, whereas this carbon right here is a secondary carbon. And so we technically only have two different types of beta carbons. And because of that, we're going to have two different types of E2 products. Okay, so let's take a look at the first elimination product, in which the bond, or the pi bond, is between the alpha and beta 1 carbon. So let's take a look. So we have a double bond here, and then there's going to be a methyl group, and then 1, 2, 3, 4. So 1, 2, 3, 1, 2, 3, 4 carbon atoms. 1, 2, 3, 4. All right. And so again, this is the beta 1 carbon right here, and the alpha carbon bonded to it, double bonded to the beta 1. And so this is one of the E2 products. And then the other one will be a double bond between the alpha and beta 2 this time. And so we're going to have a double bond here, and then 2 methyl groups. And then let's see here, we got a double bond here. So 1, 2, and 3. 1 carbon, 2, and 3. There we go. So this is an E2 product. This one is also an E2 product. So the first alkene here on the left, this is going to be the major product because it's tri-substituted. Whereas this one is only di-substituted. So this is going to be the minor product. So let's label them minor and major. This one right here is major. All right, so these are the two. Let me move this one down here so it's not confusing. All right, so these two are the elimination products for this specific reaction. And here's practice problem number 23. Draw a stepwise mechanism for the following reaction. So again, the first thing that you want to do here is to analyze the nature of, or the classification of, the alkyl halide and the nature of the nucleophile or the base. So the alkyl halide here, you can see that this is a tertiary alkyl halide. So let's go ahead and label this tertiary. And when you look at methanol here, you can see that methanol can act as a base and also as a nucleophile. And this is considered a weak base and also a weak nucleophile. So weak base and nucleophile. All right. And so because we have a tertiary alkyl halide, this can undergo both SN1 and E1 reaction. And the fact that we have a weak base and nucleophile makes that even more true, right? So this will undergo both E1 and SN1 reaction. So let's look at the SN1 reaction first. So with SN1 reaction, so I'm going to redraw the molecule here so I can show you the mechanism. So the very first step here is the generation of the carbocation. And so so the bromine atom will come off. And then what happens is we have a carbocation. So we have the alkyl, or the cyclohexane ring right here. And then a positive charge on that carbon. Oh, and we also have this methyl group right here. So this is the first step in SN1 reaction, and then the next step is the attack of the nucleophile. So we have a CH3OH here, and this will attack that electron deficient carbon atom, and then what we get is the SN1 product. So the SN1 product, we have oxygen, a hydrogen, and then a positive charge on this oxygen. And then, of course, we have a methyl group here. And so now the bromide ion will act as a base, which will then deprotonate one of the hydrogen atoms here. All right, so it's going to attack one of the hydrogen atoms. And then the sigma bond breaks, and the lone pair of electrons will move towards the oxygen. And so what we have now is an alcohol. All right, and of course, HBr, hydrobromic acid, as a byproduct. So this is the organic product of the SN1 reaction. And for the E1 reaction, so I'm just going to write down E1 right here. So what we're going to have to do is to label the beta carbons. So we have the alpha carbon right here, and we have 1, 2, and 3 different beta carbons. So let's label them real quick. So this is a beta carbon here, another one right here, and the third one right here. So these are all different beta carbons. So we can label them B1, beta 2, and beta 3. And so that means that we can have 3 different elimination products. So let's take a look at every single one of them. And so we have, again, a cyclohexane ring right here. And so the very first step in E1 is the generation of the carbocation again. So we will get a carbocation here. And then the base here, the methanol, will act as a base and will deprotonate. It will deprotonate one of the hydrogens on the beta 1, beta 2, or beta 3, right? And so here, over here, or well, not that one, the hydrogen here. All right, so we're going to have 3 different E1 products. So the first one is going to be a double bond between the alpha and beta 1. So beta 1 is right over here. So let's label this beta 1. And then the other one is going to be a double bond between the alpha and beta 3. And then finally the third one will be a double bond between the alpha and beta 2. So that would be right over here. All right, so when we compare these 3 elimination reaction products, you can see that this third one right here is tetrasubstituted. So we have tetrasubstituted, disubstituted, and disubstituted as well. So you can see that this third one is the major product. So this is the major product of the E1 elimination reaction. And so these are the main products of this specific reaction here. So we have, again, the ether right here, the alkene, and the acid.